Welcome to today's lecture. I hope you can hear me also at home. Perfect. Yes, so I'm Franka Schmid. I'm a senior researcher in the group of Professor Jenny. You're going to meet Professor Jenny next week, I think, in the lectures about the lung. Yes, a few years back, I basically took over this lecture from Professor Jenny because it's basically what I've been doing during my PhD. And so we thought it makes sense that I actually present this work because I'm most familiar with it. Yes, I'm currently still at ETH Zurich, but I will actually also transition to the group of Professor Obrist in the summer to start my own little group there, where I also still focus on blood flow in the brain. So what we will look at today is written here. So we look at blood flow and capillary networks, and we will have a specific focus there on the brain. Generally, all the equations and all the modeling which I described is not limited to flow in the brain. But yes, the brain is one example, and I think it's a very nice one and a very exciting one, simply because there is still so much unknown about the brain that I personally find it very, very exciting to work on that topic. We're going to start with a motivation, why we're interested in the brain, and also what we're trying to achieve with some simulating blood flow in the brain. I will also explain you a little bit what we know about the vasculature of the brain. And afterwards, we come to the modeling. And I will explain how can we develop a numerical model to describe blood flow and capillary networks. And then in the second half of the lectures, we're going to look at the effect of red blood cells in the microcirculation. And that is actually something which makes the whole story a little bit more interesting. Yes, so why are we interested in blood flow in the brain? And here you see an image from an MRI machine. And I guess maybe sometime during your studies or in general, you already came across one of these images here. And you can see there is this red area highlighted here. And that basically means that in this area, we have a higher neuronal activity. However, what you also need to know is that it's actually not the neuronal activity which is measured here, but in the end, it's changes in blood flow, or more specifically, changes in oxygenation that are measured in MRI. And the reason why we can actually directly translate changes in neuronal activity to changes in blood flow is that there is a coupling of neuronal activity and blood flow, which again means that if we have a higher neuronal activity somewhere, then we also have increased blood flow in this area. As I already mentioned, this is used in many different imaging techniques, and it's also used for diagnosis in pathologies. So for example, you can see that during Alzheimer, that the patients then have reduced blood flow, or you can see that during stroke, and so on and so forth. So it's really this coupling between blood flow and neuronal activity is really important, also in the clinic. I already mentioned that there is blood flow regulation in the brain. And this means that blood flow increases in the area which we use in our brain. And that actually also enabled us then to kind of differ for the different brain areas what their functional task is. And to just give you an example, you can see here in blue, that is the primary sensory cortex. So basically, if you move your arm or do something like that, that is the area in which the blood flow will increase. And by doing that, we could differ between all these different areas. So here, for example, in the front of your brain, you have the visual cortex. Oh, sorry, in the back of the brain, you have the visual cortex. Here you have the somatosensory cortex, which is responsible for feeling or like what you feel at your skin. Let's become a little bit more specific. What questions are we, for example, interested in, or why do we want to model blood flow? As I already said, there's blood flow regulation and oxygen supply. And these two aspects are actually very important in the brain because the brain only has very limited energy storage capacities. And this means if the brain can't store the energy, which comes from the oxygen and the nutrients, that we basically have to have a very robust supply of blood flow to constantly deliver nutrients. And that is, for example, also something which is different in contrast to muscles. Muscles, they can store glucose very well, and that's why there it's a little bit less critical to have a robust supply. Yes, and this also underlines why we want to understand how is blood flow regulated and how can actually the vascular network of the brain achieve such a robust supply. And one question which we're trying to understand here is which vessel type is actually responsible for upregulating blood flow. And we will look at the different vessel types a little bit later on. Another thing that we're trying to understand is actually on which scale does this regulation take place? Is it really across a whole brain area, or is it really more localized, maybe just in an area of a few micrometers where blood flow gets regulated? And by doing that, we can then again also make conclusions, basically on the neuronal activity. So how many neurons are active at the moment, how many neurons need more blood, and what happens actually there, and how do the neurons communicate with the brain? I already also mentioned diseases where it is important to understand the blood flow in the brain. And again, I just want to show you some examples. One aspect, for example, is Alzheimer's disease. So what is known about Alzheimer's disease is that the capillary networks which we have in the brain are less dense during Alzheimer's disease. And that's actually also one of the first symptoms which you can record. However, it's less clear if actually it's first the capillaries which become less dense and then the neurons which die, or if it's the other way around, that first the neurons die and then the capillary network gets less dense. So that is something which we can help with simulations. Another aspect is we can also try to model drug delivery, or what I've shown you down here, an example is what happens during stroke. And again, just very briefly, that's basically the feeding vessels which you have at the back of your head, the so-called circle of Willis. And you can see these are different feeding areas in the brain, and we have different kind of large feeding vessels, which are called the ACA, MCA, and the PCA. And for example, if in a mouse brain, you occlude the middle cerebral artery, that's how the perfusion then looks like. And you can really see that in this whole area here, we basically don't have any blood flow anymore. And of course, because of that, we also have neurons that die, and mice or patients that are impaired afterwards. Here, just another very brief example from one of the works which have been done in the group of Professor Jenny. So here we now look at oxygen transport. These cylinders which you see here, they're a little bit simplified red blood cells. The color coding of those red blood cells is given here. That is basically the oxygen saturation of these blood cells. And the tissue which is around all these capillaries, here the color coding is the oxygen partial pressure which we have in the tissue. And if we now look a little bit what we see here, we see that we have red blood cells with a very low saturation. We see that we have red blood cells like here with a very high saturation. And what you can also see that, for example, here you see it pretty well, that where we have a high oxygenation in the red blood cells, we also have a high oxygenation in the tissue around. And this shows very nicely that actually the oxygenation in the tissue is also very heterogeneous, and it's important to understand for us. Yes, so let's proceed and have a look at the vasculature of the brain. As I said, the modeling is not limited to brain networks, but still we're going to have a look at it a little bit because for some aspects of what I show you, this is relevant. Here, you just see a rough sketch of the large feeding vessels of the brain. And that's normally not the level we look at, but just that you have an idea that basically all blood comes from your neck, then to the circle of Willis, and afterwards we reach this level here. And this is basically the level of the pile vessels. And the pile vessels, they are located at the surface of your brain. And here in red, you see the arteries, and in black, you see the venules. And you can already see that these vessels are kind of everywhere, that they also get a little bit thinner as they ramify. And that just means that the pile vessels are really the vessels responsible for distributing the blood to all different areas of the brain. Here you see a comparable image of the mouse brain. Generally, you have the same pictures. Here would be the inflow, and the further down you get, the more the vessels ramify and the more deliver the blood to different areas. Another thing which you might have already spotted in the picture before is that there are differences, for example, between the brain of the primates, so monkeys and humans, and the brain of the mice. And the difference is that you have these folds here in the human brain, which you don't see in the mouse brain. And that is actually something which I didn't know as I started doing my PhD, but which I think is kind of cool because actually this dark area here is where most of the thinking and everything is basically done. And just by having these folds, we basically increase the surface area of, well, but that we can use for thinking or doing tasks. And the mouse doesn't have this, this aspect. But besides that, the networks between mouse and monkey are pretty similar. And we're going to have a closer look at them here. So again, as I mentioned, at the surface of the brain, we have these pile vessels, which distribute the blood. And then afterwards, we have these perpendicular vessels, which are the descending arteries and the ascending veins. And in between these vessels, we have the capillary bed. And as you can see here, the capillary bed is really, really dense and contains loads of different vessels. If we look deeper here, you can see that here the structure is a little bit less organized, which of course makes it more challenging to study the flow here. And that's why many simulation studies actually focus at this area, which is, as I said, this dark little sketch down here, so the outermost layer of the brain. Another thing which is pretty cool and which is available since recently, that imaging techniques improved such that we basically now have really a whole reconstruction of the microvasculature of the mouse brain. And you can really see in such a mouse brain, we have millions of different vessels. And yes, that's also very interesting to simulate and to study what happens there. To give you an idea about the length scales that we have in the brain, or the scales of the vessels, we've been already briefly talking about the different vessel types. So the pile vessels at the surface, they have a diameter larger than 30 micrometers, more or less, but they can also be up to 100 micrometers. Then we have the medium-sized vessels, that would be those penetrating vessels. They have diameters from 7 to about 32 microns. And then we have the smallest vessels, the capillaries, which have diameters smaller than 7 microns. And that's actually also the vessels that we're gonna focus on regarding the modeling. So which questions do we have regarding the vasculature of the brain? Or why is that also interesting for us? So first of all, as I said, it is important that the network is very robust and that it's able to deliver oxygen everywhere. Another thing which we have to keep in mind, if we have so many vessels, the blood still needs to be able to pump everything through. So somehow the network also needs to be optimized regarding the flow resistance of the entire network. Yes, another aspect is the development and the plasticity of the network. So how does this network develop in the first place? And for example, also again, if you had a stroke or something, how well is the network able to adapt again to the changes or kind of, yeah, grow vessels again, such that you can maintain perfusion. And the last aspect, which I mentioned here, is again the regulation of blood flow and at which level it is regulated. And here the big questions, which is still actually not entirely understood, is if it's those penetrating vessels, the arterioles, which are responsible for regulating blood flow, or if it's the capillaries that also contribute to regulating blood flow. Almost certainly it's probably a mix of both, but still it's not entirely clear to differ that. Here I've been now just talking about the topology, but as you can guess, the topology and the flow, they go hand in hand. So in order to kind of understand the topology of these networks, we also need to be able to understand the flow field in these networks. So yes, let's start looking at the flow in these networks, or what is important here. And as it's often done in fluid dynamics, the first thing which you do is that you look at the dimensionless numbers. And I guess you covered most of them already in the course of these lectures, but let's briefly go over the ones which are relevant for this context. So first of all, we have the Reynolds number, and the Reynolds number is basically the ratio between the inertial forces and the viscous forces, and can be computed for pipes from the viscosity, the velocity, and the diameter of the pipe. And in the case of these microvascular networks, at the level of the pile vessels, we have a Reynolds number, which is about 1. And in the capillaries, the Reynolds number is very, very small. And it's, much smaller than 1. And this means in the end that the inertial effects can really be neglected in these networks. So we really have a Stokes flow, and inertia doesn't play a role for our simulations. And that is really something which is important to keep in mind if we talk more about the modeling of these networks. The second number which I want to mention is the Wormersley number. Again, I think you heard it already as you were talking about flow in larger vessels, but the Walmsley number is a dimensionless number, which looks basically at the pulsatile flow frequency in relation again to the viscous forces. And this is relevant because, of course, we have the heartbeat, and so we need to know, do we need to resolve the pulsatile utility of the flow? But again, because the viscosity, or because the calibers are so small, the viscosity plays such a big role that at the level of the capillaries, we can also ignore the Walmsley numbers and the pulsatile effect. If we look at larger vessels, when pile vessels actually, you would still see the heartbeat to some extent. But yes, again, it doesn't play a very large role in these small networks. The third number which we're going to mention is the D number, and the D number is relevant if we think about the capillaries, which had a very tortuous structure. So again, here we need to know, do we have to account for this tortuosity or not? And generally, the D number compares the inertial forces and the centripetal forces, but I guess you can already guess. But the viscous forces are again so large that also here we don't have to account for the centripetal forces, and we can basically neglect vessel tortuosity and simply assume that our vessels are more or less straight pipes. And yeah, we don't have to resolve all the curves for our modeling. So how would we now proceed if we want to simulate the flow? Here you just see an example of a capillary, and as you probably know from fluid dynamics, or normally in such a tube we have a parabolic flow profile if we are in the laminar regime. And as I said, we have very small Reynolds number, and that also means that the Navier-Stokes equation reduces to the Stokes equations, where we have the Laplacian of the flow, so the viscous forces and the pressure gradient. And here on the right, you see the continuity equation with the divergent of the velocity. And if we then now take the divergent of this equation, we end up with the Laplacian of the pressure. If we want to continue and really resolve the flow in such a capillary, we also need boundary conditions. And that means we need to know what we have at the inflow and at the outflow and at the walls. And what is commonly done there is that you have a constant pressure value, and that you assume a constant outflow rate here. And the same basically is what you do at the walls. Here again, you know the wall isn't moving, so that is one boundary condition, that you have zero flow, and again that you don't have a pressure gradient in normal direction at the wall. If you set up the simulation like this, you really need to discretize the whole area. So that means you have different grid cells in there, and you really compute this flow profile. And yes. Another thing, if we want to now add in red blood cells, that means, we can see that in the video here, I'm going to show you that, the red blood cells aren't stiff, they deform, well, quite heavily, as you can see here. And this, of course, means then that we would actually not only do a flow simulation, but that we would also need to resolve the structural deformation of the red blood cells. So in that case, you would need to do a fluid structure interaction simulation to describe this whole motion of the red blood cells. In addition to that, you can also see that a little bit here. Each of these arrows is basically located in a grid cell, and that means that we would also need a very, very fine grid resolution in order to run these simulations. All in all, this, if you would set up our simulation or our model like this, that would be very computationally expensive. And the question arises, is that really what we want to do? Because what our primary goal is that we can compute in such a network like that, which has thousands or even millions of vessels. We want to compute the flow rate in every vessel. And we also want to know the red blood cell concentration in every vessel. And yes, and to attain this goal, we actually don't need to set up such a fluid structure interaction simulation, but we can take an easier approach by assuming basically that we have Poisson flow in every vessel. And in addition to that, by also simplifying the red blood cell motion a little bit. And we're going to look at how we do that in the next few slides. So the first thing what we do, as I said, we assume that we have ideal tubes. So that means we don't have tortuosity, and basically the vessels are just connected one tube next to the other tube. Here we still have the tortuosity, but in the end, that is just well, a detail. We don't necessarily have to consider the tortuosity here. And we also know that we have a Reynolds number that is very small. That means we can really simulate the flow by Poiseuille's law, which we're going to look at in the next slide. Simplifications which we do is that we neglect the deformation of the red blood cells, which makes the simulation much more doable or feasible computationally. And one thing which we do in the first part of the lecture is that we also assume that we have a constant volume fraction of red blood cells, what is called hematocrit. In the second lecture, we're going to drop that simplification, but for now we assume that in each vessel we have the same volume fraction of red blood cells. Yes, so how do we solve the flow in these vessels? And again, we have the Reynolds numbers, which are very small. And if we're in the laminar regime, in a pipe, we have this parabolic flow profile. And this in the end means that the pressure drop is proportional to the length. And this is exactly what is given by Hagen's Poiseuille's law, where you have the flow rate here, and you see the pressure drop is here, and the pressure drop is proportional to the length. So what is the term in front here? That is basically the vessel resistance. And the vessel resistance, just gives you kind of the scaling factor by how much does the pressure drop per length scale. Sometimes the resistance is also called transmissibility. So that's just basically the transmissibility is the inverse of the resistance. And the nice thing about the Hagen-Poiseuille law is basically that it can be directly derived from the Navier-Stokes equation. If we know that we have laminar flow, and if we also know that we have a pipe flow, so basically that we have a radial flow profile. The resistance can also be interpreted in such a way that basically we have the shear stresses in the flow, and that if you basically integrate the shear stresses over the cross-sectional area of the tube, that basically you also obtain this term, which is then the resistance per unit length of flow. One aspect which I want to highlight about the resistance is that the resistance, that's again this aspect here, that the diameter to the power of 4 is the driving factor for the resistance. And if you now think again about the aspect which I mentioned before, the flow regulation, where we have diameter changes of the different vessels, this really underlines how important the diameter of these vessels is and how large the changes can be if you just have a very small change in diameter in one of these vessels. Let's continue to look a little bit at how the flow looks in these networks. And we're going to look at the flow field at a bifurcation, because so far we said we just have pipes which are connected with each other. But of course, you have this bifurcation here, and we have to have a closer look at what actually happens to the flow at such a bifurcation. Here we now look at the flow where the Reynolds number are larger than 2. So we still have some inertia playing. And what you then see at the bifurcation here is basically that you get such a recirculation zone here of flow separation. And this occurs because of the inertia, because the turn here is too sharp that basically the flow detaches and that it doesn't follow directly the bifurcation, but that you have this little area here where you have the recirculation. However, again, if we look at flows where the Reynolds number is very small, so if in the Stokes regime, the inertia doesn't play a role, and then the flows streamlines look like this. So the flow can really follow exactly the topology of our bifurcation. And this again is relevant because actually Hagen-Poiseuille's law is only valid if you have a fully developed flow. So that means not directly at a bifurcation or at an inlet or something like that. But we again don't need to worry about that because we are in this area here. So yeah, Hagen-Poiseuille's law is actually also valid across the entire length of the vessel. So much about flow in one vessel. How we're going to proceed now to solve the flow in an entire network. And we're first going to look at a single bifurcation here. That's a little bit how we normally draw these networks. We have our different nodes or bifurcations, and we have the vessels that connect these bifurcations. And we have a transmissibility for each of these vessels. And then we can simply compute the flow rate, for example, in vessel 1, 2, from the pressure drop, which we have across these points, and the transmissibility of this vessel. And we can, of course, do this for all these different vessels. And here at node 2, we know that we have the mass balance needs to be fulfilled. That means everything goes in, also needs to go out. What happened? Oh, well, there it is again. Yes. And a thing which is actually very interesting here is that the way how we solve these systems is actually very comparable to electric networks, where we have resistors, and the resistors are connected also at bifurcations. So it's basically really exactly the same as an electric network, how we can solve the flow in these networks. Here we can also think a little bit further. So for example, instead of just having a connecting point here, we could also have a capacitor at a bifurcation or at a connecting point. And this would then mean, in the case of an electrical network, that electrons could be stored at this location. In the case of our biological network, this would simply mean that basically the vessels aren't stiff, but they're tensile, and that we can also have flow, which is kind of stored here, or the volume basically of the vessel changes here. We're also going to talk about that aspect a little bit later if we set up our equations. So let's go from our bifurcation to an actual network. Here you see now a few more nodes which are connected by each other. And the first thing we're going to look at is the nodes which are at the outside of our network. And here we can see the blue ones. Those are basically the nodes where we assign pressure boundary conditions. So there we know what pressure value do we have. And the green one is a node where we assign a flow rate boundary condition. So here we know already what flow rates or what pressure values we have. In addition to that, we have these internal nodes. And for the internal nodes, that's basically our goal. Here we want to compute the pressure values. What we have in addition to that is that for each of these vessels, we know the diameter and we know the length. And because of that, we can compute the transmissibility of these vessels. I already mentioned that in that representation, in the end, a node doesn't really have a volume because it's just a point, but we can assign the node a volume. And the easiest way to do that is that we just add basically half the vessel length of all the adjacent vessels, and that ends up then to be the volume of node 1, for example, here. So how do we proceed? We now want to compute the flow rate and the pressure in this network down here. Again, here you see our goal and very briefly what our assumptions are for now. And here you see a little bit the equations which we have or what we know about the network. So again, we know the transmissibilities. We know that we compute the mass flow rate between two nodes from the pressure drop and the transmissibilities. And another thing is that we have the volume of the node. And here, the volume can be set constant. We're also going to do that later. However, the volume could also be a function of the pressure, because you can imagine if you have a higher pressure in the vessel would expand a little bit, or the volume could also be a function of the pressure change in time. How do our equations now look? And we're going to look at node 1 to start with. So here you again see the volume and the volume change over time. And then you see the 4 different flow rates, which are basically the flow rates of the 4 edges that are attached here. And because of the continuity and the mass balance, that's going to be equal to 0. We can look at another node. So we have node 2 here now. And node 2, for example, just has 3 adjacent edges. And because of that, we just have 3 flow rates here. And we can also look at node 5, which is located up here. And here now, in contrast to the other nodes, we are not at an internal node, but we are at the boundary. And that's why here on the right-hand side, we actually have one of our boundary conditions, so a flow rate, which is going to be assigned. As I said, mostly in the capillary bed, there aren't very large changes in the volume of the vessel. And moreover, if you would want to model this, you would also need to know a relation. So how does the vessel volume change in function of pressure? Or how does the vessel volume change in function of the pressure over time? And that's just 2 things which are actually very difficult to measure. And because of that, for simplicity, what is mostly assumed is that the volume doesn't change over time. And that simplifies our equations also quite a bit. So we can simply just cancel out this part here. Then we can use our equation for the mass flow rate and plug this in, and we end up with these three equations for the three nodes which we just looked at. And what you can already see now is basically that we have the transmissibility always here, and here we have our pressure drop, and that basically the only unknowns in these equations are now the different values for our internal nodes. And if we do this now for all our 8 internal nodes, we end up with a system of linear equations like the one which is shown here. And what you see here is basically we have for the 8 different internal pressure values, we have 8 different equations. Here again, you see the 3 which we looked at before. So for example, here in the first row, you have the equation for the first node, where you see here, we have the sum across the P1s, which is basically here, the 4 different entries. So the sum of all the neighboring pressure values. And at the other points, so between P1 and P2, we have this value here, and P1 and P3, this value here. And that's basically how this looks for an internal node. If we now look at, for example, node 5 again, this is written here. You can again see that now on the right-hand side, we have the flow rate instead of 0 here, and the rest is equivalent. So always at the node which we're looking at, we have the positive sum across the neighboring nodes of the transmissibility, and across the neighboring nodes, we have these negative values. Let's look at another example. For example, one of the nodes which is adjacent to a pressure boundary conditions. And here, then on the right-hand side, we can basically use the transmissibility, which we have here, and the pressure value, and that's basically what we end up on the right side here. So in the example which I showed you here, we just have 8 unknowns and yes, 8 equations for that. And that's actually rather simple to solve. If you have a small system, you can just directly invert this matrix, and then you obtain all the pressure values for your system. But however, as I mentioned before, in those whole brain networks, we have millions of different nodes. And then sometimes it can actually be more efficient to use well, iterative methods or something like that to solve your linear system of equations, simply because these systems aren't very complicated, because it's still a linear system of equations, but nonetheless, if they get very large, it might be more efficient to use some more advanced numerical methods to solve the system of equations. Again, we now know how we get our pressure values here, but we also want our flow rates, but then we can just go back to the equation which we have here. And basically from these pressure values and the transmissibilities, we can then also directly compute the flow rates in these networks. Yes. So far, we just looked basically at the flow rate. But as I said, another thing which is generally interesting is also nutrient transport in these networks. And we're going to look a little bit how we would add a nutrient transport in the simple case now. So what changes now if we set up our equations for the nutrient transport is, again, that we basically now have a term for the mass of the nutrient again here. And maybe just to clarify, the C is the concentration of the nutrient. And those what we see basically here is now the mass balance for the nutrient. Before we were looking at the mass balances of the flow, but now in addition to that, we have the mass balance for the nutrients we're interested in. And the mass of the nutrient changes over time because it is transported through our system. And this is basically what is impressed here. So we have the volume of node 1, we have the density, and we have the concentration of the nutrient. What we see here again is the sum over all the flow rates. And this is basically the flow in these 4 vessels. And you can also see that here's a change to how we set up our equations before, because now we also have the concentration written down here. And now we could ask, well, what concentration do we plug in here? Because basically we're interested in the concentration along this vessel. And what is commonly done here to solve such a system is that you use a so-called upwind scheme. And that means if you know that the flow is coming, for example, from C3 to C1, you would simply use the concentration which we have at node C3. For example, if we know that the flow comes from C1 to C2, we would use the concentration which is stored here for the concentration along this edge. And this is basically always done based on the initial state. You look which flow directions do we have, and based on that, you decide which concentration you use for which vessel. If we now assume again that our vessel volume is constant, we can kind of pull the volume out of our equation, and we end up with an equation which looks like this. In addition to that, I forgot to mention that before, we have a source term or a sink term here, and that could, for example, be that the tissue consumes the nutrient there, or that, well, that waste products of the tissue are actually given back to the vessel. So that is something which you can add in here, and that would occur then exactly at this location of this node here. Yes, so we basically have now this system of equation, and as before, we can set up the system of equation for each node. However, what we need to do now is, because we have a time derivative here, that we need to integrate this equation in time. And the easiest way to do that is that we use the explicit Euler scheme, and the explicit Euler scheme basically says that we can approximate this derivative by taking the concentration at time n+1 minus the concentration at time n, and divide it by the time step that we use. So just to clarify again, so now the superscripts are basically the time points. So are we at time point n or time point n+1? And the I is basically the node that we're looking at. Yes, so if you use basically the Euler explicit and plug it in for this term here, and then kind of transform the whole equation such that you have the concentration to the new time point at one side, that's the equation which you end up with. So what could we assign for our source or sink term, which we have all the way to the right? So just to give you an example, it could simply be a diffusive exchange with the tissue. And then we would have, what would matter here is basically the surface area of the vessel, so kind of the whole exterior part of the vessel. And in addition to that, we have an exchange coefficient, and we also have the concentration outside of our tissue. And yeah.
In this equation, the explicit Euler equation, in the right-hand side, we took all the parameters in time step number 10, yes?
Yes, exactly. Yes, it's not very well written, but yes, all of them, they would be in time step n. Yeah, on the right-hand side, it's really everything is to time step n. Yeah.
And they are variable, yes? Concentration varying over time.
Exactly. So that you have a concentration. So basically, you would start, for example, with 0.0, your initial field where you have 0 concentration everywhere, and then that's everything which you would have on the right-hand side. And then based on that and the flow rates, which you know from solving the flow field, you can then compute how the concentration would evolve to for the next time step. So I mean, in that setup now, the flow rates would be constant, so the flow rates don't change. So you have one flow field, and you can just basically simulate how the concentration evolves over time. So you start from 0, and then it increases. For example, if you have an inflow here, it would increase here. Yes, and that's basically then how the concentration changes over time.
Is there any alternative that can solve implicitly?
Yes, totally. I mean, in the end, that is just the easiest way to do it. But you can also solve it implicitly, and that sometimes has advantages for the stability of the system. But then, I mean, all that happens is basically what you put in here changes, and then you need to transform the equation again to basically end up in this situation where you have your new concentration to the next time step here. And if you, for example, use an implicit Euler, you just get a little bit different looking right-hand side, because just from the default formulation, you would also have the concentrations from the next time step. So you need both concentrations basically from the next time step and the last time step to compute the next time step. Exactly. And if you do that, it just looks a little bit more complicated basically on the right-hand side. But you could also use an implicit Euler scheme here or other time integration methods. In the end, the approach is similar. The only thing which changes is basically how your right-hand side looks, and it can look rather easy like it looks here, or it can look more complicated if you use an implicit Euler scheme or other time integration schemes. Exactly. Yes, and maybe as you mentioned as well, you could also, for example, have some kind of coupling, for example, that the concentration affects your flow resistance or something like that. And then, of course, you would need to solve both iterations, well, again and again, because the concentration would then kind of give a feedback on the flow rates. And then, it just gets a little bit more involved and more equations that you need to solve. But in the end, that's the basic idea how you would solve such a system of equations. Yes, and actually also, if you're going to look at the red blood cell later on, that's actually also what you need to do there, because the red blood cells, as you probably also already heard in the lecture about blood rheology, they affect the resistance of the vessels, and because of that, you basically need to account for them and do this step over and over again and change the equations more frequently, compute the equations more frequently. And yes. And so the final step, which is basically listed here, is that we now need to plug in this term for our source term here, and in the end you end up with this equation, and you can set up again a system of linear equations and can simply solve that for the different time steps or for as long as you want to, or you're interested in your concentration in the network. Yes, so again, just a very brief animation of how these networks look. And as I already said, we know now how we can compute the flow rate in these vessels, and we also know how we can could compute nutrient transport in such a network. But one aspect which we didn't talk about yet is basically the boundary conditions. So far, I just always mentioned, well, we know the pressure values or we know the inflow rates here. But actually, as you can see here, that is just a very small chunk of such a network. That's actually a cubic millimeter of such a network. And you can see that we have many dead end vessels everywhere and actually many inflows. And if you remember, that is just somewhere in the mouse or the human brain. So actually, it is not very easy to actually know what kind of boundary conditions do we want to prescribe at these vessels. And that's actually one aspect which we're going to look at in the second part of the lecture. We're going to look at how can we actually assign appropriate boundary conditions at all these inflows here, or what would be a good approach to do that. And the other thing which we're going to look at in the second part of the lecture is the transport of the red blood cells. So far, everything was pretty easy because we just have to solve one linear system of equations to get the flow rate in every vessel. But the red blood cells, they affect the resistance of the vessels. And on top of that, the red blood cells actually also don't behave similar than the plasma flow. And because of that, yes, we actually need to solve the system or really transport the red blood cells through the network and solve the system a couple of times to actually really mimic all these effects that we have in this system. And yes, I think I'm through. Yes, so as I said, so in the second part, we now want to look at how do we assign boundary conditions for these networks and how can we describe the motion of the red blood cells. And again, as I said before, our goal is to know the distribution of the red blood cells in the entire network, but we're less interested in how do the red blood cells deform. We really just want to know how many red blood cells do we have in the different vessels, and how can we attain this goal? So here again, our two goals for the second part of the lecture, what we're going to look at. And we're going to start by looking at the boundary conditions. And here you see the network in which I actually did most of the simulations during my PhD, and these different spheres which you see here. I think I didn't switch on the video, right? Yes, now you see me at home as well, a little bit dark, but still. Anyways, so the spheres which you see here, that's basically all the locations where we have an open boundary and where we need to assign a pressure or flow boundary conditions. The red spheres are the ones which we are at the pile surface. And as you can imagine, if you have the pile surface, which is really close to the surface of the brain, it is still somehow possible to actually do some pressure measurements there. And here you see some examples. It's all very old studies from the 80s or something like that. But nonetheless, you can see a little bit that we can measure pressure on the arterioles and also on the venules. And what you see regarding the arterioles is also that the pressure which we have there depends on the diameter of the arteriole. And that also makes sense because you have the larger arterioles very close to the inlet. And of course, there you have a higher pressure. And the further you go down the network, the more pressure drop you have, and the lower the pressure values get there. On the venue side, this is actually also interesting. Here, we don't have a very large dependence on the pressure values. That's also why we can make it simple and simply assume that at the venule outlets, we have a constant pressure, and at the pile inlets, we fitted such a function such that we can have a diameter-dependent pressure values at these inlets. So well, now we know what to do at the red spheres, but we still have all these capillaries here where we doesn't work. There we let me switch that off again. Everything went so smoothly in the first half. Of course, now all the problems come. Yes, so we still don't know what pressure values to assign at the capillaries, and we need to come up with a solution for that. And what we do here is basically that we make use of the hierarchical topology of these networks. If you remember what I showed you in the first half, is that we have the pile vessels at the cortical surface. Then we have these perpendicular vessels, which dive down here, the arteries and the venules, and we have the very dense capillary bed in the center of the network. What we do now is basically that we construct a very large semi-realistic network, which we'll then use to assign the boundary conditions. So first of all, how do we construct this network? Here, what we do first is that we generate a network of penetrating trees that is shown here. And these penetrating trees, they are in our case from penetrating trees that have been measured in the red. So it's really realistic penetrating trees, which we just distribute over a very large area. In addition to that, we have a capillary bed, and here we make some simplifications because, as you can guess from the images here, it's very hard to actually measure all capillaries correctly, and thus we simplify this approach, and we have such a stacked honeycomb network. The good thing about this honeycomb network is actually that the bifurcations are all bifurcations, so that means it always connects 3 capillaries, which is in line with what we observe in vivo. And thus it's a good approximation of a capillary bed. And the third component of our big compound network is then our realistic network, which I showed you before, which we plug into the center of this network here. And what we do now is that we use this very last networks, and we now only have inflows at the surface here. And here we assign the diameter dependent pressure values, as I shown you before. And then we do a simulation where we don't track the red blood cells, but we assume a constant hematocrit. So basically just like I described in the first lecture. However, from that, we then get pressure values in the entire vasculature, and we can then use these pressure values to assign them at the capillaries, at the capillary open ends, which are marked by the spheres here on the right-hand side. And actually, we tried that a little bit. So we could rotate the network, or we could construct different compound networks, and actually it doesn't play a very large role well, what pressure values we get here. So that's a very robust approach to simply plug our realistic network into a large compound network to get physiological pressure boundary conditions also at the capillary in and outflows. As I said, the next thing which you want to do is to look at the red blood cells. And what is interesting about the red blood cell is basically what is summarized here. So there are three red blood cell related flow phenomena in the microcirculation. The first one is the bifurcation rule. And the bifurcation rule is basically that the red blood cells distribute with a different ratio than the bulk flow. The second one is the effect on the transmissibility, but it's also called Fourier's-Lindquist effect. And the third one is the red blood cell flow with a different speed than the bulk flow again. You also probably heard of these effects a little bit. We're going to revisit a little bit what each of these effects means for our modeling now. And what is interesting here as well is that these effects, they are known probably since the 1990s, so a very long time ago. However, it hasn't really been looked into what role they play for the nutrient supply or what role they play for the blood flow in these networks. So we know these effects, but it's less clear what role they actually play. And I'm going to explain a little bit what role these characteristics might play. So first of all, of course, we need to account for these effects in the simulations, because now we have actually two phases for our simulations. We have the plasma phase and we have the red blood cell phase, which behave differently in our simulations. But of course, they also play a role for blood flow regulation, because you can imagine that if you have a capillary with many red blood cells, you will have more oxygen available than if you have a capillary with basically no red blood cells in it. And of course, this also plays a role for the robustness of oxygen supply. And here again, I just show you two examples from literature and from work at our institute. So here, just an example from measurements in the mouse, where you again see the hematocrit, so the volume fraction of red blood cells, and the tissue oxygen saturation. And you can clearly see that the higher the hematocrit is, or that there's tendency that for higher hematocrits, you also get a higher tissue oxygenation there. And here's another example from a simulation. Here you see the different probe locations, so close to the vessel wall, a little bit further away and far away from the vessel wall. And you can really see here the oxygen partial pressure again, and you can really see how if a red blood cell passes by, you get such a spike in the available oxygen availability. And of course, again, this also plays a big role for how much oxygen do the neurons actually get at the different locations. You also see here, for example, that the entrance of the capillary, we have a higher oxygen level than here at the outflow. And that is also apparent if you compare this red blood cell here and the one here. Of course, the red blood cell discharge a lot of oxygen, and thus it has less oxygen available if we go further down to the venule end of the capillary bed. Let's look at the first of these red blood cell related flow phenomena. And here we want to look at the impact of the red blood cells on flow resistance. And what you see here again is the parabolic flow profile, which we know already from the first part, how you would expect it for classical Hagen-Poiseuille flow. What happens now if we have a red blood cells in this network? Red blood cells, they have an average, I think in the mouse, the red blood cell disc has about a diameter of about 8 microns. However, the capillaries, they can be as small as 4 microns. So the red blood cells really have to deform heavily. And that means that they tend to travel in the center of the capillary. And it also means that here at the side, we have very, very steep gradients in velocity. And these steep gradients in velocity means that we have a very, very large wall shear stress here. And this again means that, of course, here we have a larger pressure drop per unit length than we have at a location where we don't have a red blood cells. And that is also what is depicted a little bit schematically in this plot down here. So for the case where we don't have red blood cells, our slope in pressure drop isn't as steep as for the locations where we have a large slope in the pressure drop. And of course, in the end, it all depends how many red blood cells do we have here, and that's going to define how large is our flow resistance in these vessels. And that is also what is written down in this equation here. So here, the Rij is basically the resistance if we wouldn't have any red blood cells, so simply the resistance which comes from the diameter and the length of the vessels. And this is multiplied by the hematocrit of the vessels and a factor beta, which basically is just, there are different ways to define this factor, but in the end, it just means the hematocrit increases the resistance of the vessels. That means the more red blood cells we have in the vessels, the larger the resistance of the vessel will be. The next thing we're going to look at is now the bifurcation rule. So that means that the red blood cells distribute differently than the bulk flow. And here we differ between capillaries and the larger vessels. Here you see a little movie, how the red blood cells behave at a small bifurcation. And what is interesting here is, again, you first of all see that we have a single file flow. That means each red blood cell follows after another red blood cell. And that makes it a little bit easier for our simulations, because we know that basically one red blood cell arrives, and then we just have to decide for this one red blood cell what happens here. However, if we look at larger vessels, the flow looks like that. And here you see we don't have a single file flow. So the red blood cells interact with each other, and it's much more difficult to guess for a random red blood cells, is it going to go right or is it going to go left? That is a little bit easier in that case here. For both scenarios, different solutions are available, and we're going to look a little bit how we can treat both the single file flow vessels and also how we could treat a little bit larger vessels to describe the phase separation or the bifurcation rule. Yes, and what is let's go here. Yes, and this effect is also called generally the Zweifachung effect, and what holds across all vessels is really that the red blood cells, they are attracted by the vessel which has the larger flow rate. So if we look at this example here, in that branch, we have a smaller flow rate than in that branch, and that means that if a single red blood cells arrives here, that it tends to be pulled into that branch. And of course, this is partially due also to the deformation of the red blood cells, that it just gets kind of pulled and elongated into that direction. Yes. If we now look at very, very large vessels, what we would generally see is that here in the schematic, we have the fractional blood flow on the x-axis and the fractional red blood cell flow on the y-axis. And in very large vessels, you actually don't have this effect. So in very large vessels, the whole biphasic flow, so red blood cell and blood flow, behave similarly than the red blood cell flow. So if 50% of the blood flow goes into branch A, also 50% of blood flow goes into branch A. So it's really exactly the same. So here you don't see that effect. But the smaller the vessels get, the more pronounced this effect will get. And we start by looking at the very, very narrow vessels where we really have single file flow, like in the movie, which I showed you before. Oops, like in this one here. So really vessels where we have single file flow and where one red blood cell arrives after another at the bifurcation. And again, as inertia doesn't play a role here, the only thing that matters in that moment is really in which of the two branches do I have the larger pressure gradient. And this, if you think about again about the schematic, that is how it looks like then. So we really have this kind of step function here where we see if the flow, the blood flow is below 50%, all red blood cells go into branch A. And if the flow is above 50%, all red blood cells go into branch B. And that's actually also very helpful for our modeling, because we can directly use this description if we want to model the bifurcation rule or this phase separation in capillaries. If we look at intermediate vessels, where we have kind of some multi-file flow, not too large multi-file flow, again, a little bit like the second video, which I showed you here, the one on the, sorry, the one on the right. So it's a multi-file flow, but it's still maybe just 2 or 3 red blood cells next to each other. That's kind of the intermediate regime. And in this intermediate regime, we have a situation which looks more like this. So we have these so-called S-curves. And these S-curves, what you see here is basically, we have again 2 daughter vessels, daughter vessel alpha and daughter vessel beta. And we have again the fractional blood flow and the fractional RBC flow. And here you see now again that, for example, if we have 50% flow separation, it will depend on the diameter of the vessel. So in that case, vessel beta has a larger diameter, which means that the the force which pulls the red blood cells into vessel beta is larger, and that we have a larger fraction of red blood cells which get pulled into that vessel. So if we would want to simulate these intermediate sized vessels, we would need to know these S-curves, and there are actually empirical relations around which have been measured also in the 90s, and which you can use to simulate the bifurcation rule in these vessels. But as I said, we are mostly interested in capillaries for now, so we can simply go with this rule here, where if the flow rate in one vessel is higher, all red blood cells go into that vessel. So what changes now in our simulation algorithm in comparison to what we did in the first lecture? So the first thing which we need to do is we need to start with an initial location for our red blood cells. And here we just assume, that's what you see at the beginning of the video, or you see it now. We just assume basically that the red blood cells are distributed homogeneously. So in each vessel, we have the same hematocrit. What we do next is now that we compute the transmissibility or the resistance of each of these vessels. And we do that by computing the normal resistance, so without considering the red blood cells, and then we add in the hematocrit and the effect of the Farius-Lindquist effect, so the increased resistance which comes from the red blood cells. We can then again set up our system of equations and solve the pressure and the flow field. Now we know all the flow rates in every vessel, and if we know the flow rate, we can now propagate our red blood cells. Because for each red blood cell, let's pick one which is close to a bifurcation. I don't know, maybe this one. We know now the 3 outflow rates which we have here, and then we can simply assign the red blood cell to the next vessel where we have the highest flow rate. And then again, we get a new distribution of red blood cells, and we can basically continue from point 2 onwards until we until we reach the end, or a more or less steady state distribution of red blood cells. So let's run the video again. Yes, and what you see here, what happens now is basically that we get an accumulation of red blood cells here in the corners of the networks, that we get more or less a highway of red blood cells in the center. We have different flow speeds. Here the red blood cells travel slower than the ones in the center. And in the end, the networks that used to be very homogeneous before suddenly turns out to be very, very heterogeneous. And the reason for that is basically this interaction between the resistance, which increases in response to more red blood cells being around, and the bifurcation rule. So these 2 local rules, which then basically cause that we get these global effects on the network level, so that we get demixing of the blood, and also that we get this RBC highway and this RBC traffic jams at the site. And of course, you can now say, well, I guess such a network wouldn't be very good to have in our body, because ideally we want the red blood cell distributed more or less equally throughout the network. We don't want such traffic jams, and we don't want areas where they move super fast. And that's an example that this networks wouldn't be a perfect one. And I think that's also what you will be addressing in the exercise, is basically to think or come up with an approach how such a network would need to look, that we get a homogeneous distribution of red blood cells, because that would just be way more robust for delivering oxygen than this one here, where probably these red blood cells, because they move so slow, all the oxygen is discharged, and these one, they move so fast that actually they don't have time to discharge all the oxygen. Thus, this network definitely isn't a good one to have in the body, but it's a good one to demonstrate these strong global effects, which you get from the interplay of the effective resistance, Farius-Lindquist effect, and the bifurcation rule. Now let's look again at this interplay on a little bit more local scale, namely on the scale of 1 bifurcation. So here we have such so-called 2-branch network, which is completely symmetric. So we have the same diameter and the same length of vessel in the active branch and the passive branch, how it's called here. And that also means that we have the same number of red blood cells here, and the same flow rate in both branches. If we now dilate the upper branch, what we get in the immediate response is that we get an increase in flow rate here. And that also means if we think about the bifurcation rule, that we get an increased number of red blood cells that travels into that branch. And if you think now further, now the second rule kicks in, because if you think now again about the number of blood cell increase, this again means that if we have more red blood cells in the dilated branch, that actually we also get a higher resistance of these vessels. So what we end up again, if we reach a new steady state, is basically that we have a higher number of red blood cells in this branch. And again, we have the same outflow rates in two vessels here. And that is what we call the so-called self-regulation that occurs at basically every bifurcation, simply because we have these two effects, the bifurcation rule and the Farrier-Lindquist effect happening at the same time. Of course, there are some limitations which you have to keep in mind, because in order for that to happen, one thing that needs to be there is that you have sufficient red blood cells to kind of increase the resistance sufficiently that you really get this flow balancing here. And of course, if the changes are very large, you won't get a perfect flow balance here. But in the end, at every bifurcation in capillary networks, there's a tendency that you get this balancing of outflow velocities here. We're going to look at that in another example. Again, we have this network here, and we just picked a random bifurcation here, where we have two inflows and two outflows. And what you see in the sketch here is basically the outflow velocities that happened at this location. And the first thing which you see, which is actually also very interesting, is that both velocities fluctuate quite strongly. And this occurs simply because our red blood cell distribution is constantly changing. And no matter if the red blood cell distribution changes down here, every change in the distribution of red blood cell will have an impact on all flow speeds in the entire network. And that is why you get this heavily fluctuating red blood cell speeds in this network. Yes, so what we see here now is basically we ran the simulation and we switched off the bifurcation rule. So that means we switched off that the red blood cell behave differently than the bulk flow. So in this simulation, the red blood cell behave exactly the same like the bulk flow. And what you see now is that the velocities are quite different. If we now switch on the bifurcation rule, we look exactly at the same bifurcation, you can see that if the simulation runs a little bit and if we reach our steady state, that now the velocities, they are more or less in the same order of magnitude. And that simply occurs because the red blood cells are distributed in such a way that you have this balancing, and that the red blood cells are pulled into one branch, they increase the resistance, and then they are then they're pulled in the other branch, and you have this flip-flopping, and you get this balancing around one mean velocity which you have at this bifurcation. And again, that's actually also something which is very nice and very useful about simulations, because we can just do these trial experiments and just switch off something and see and analyze the effect, which is difficult to do if you look in a living animal or something. And you can nicely play around to understand these effects a little bit better. Yeah.
In this diagram, the blue one and the red one are both the mean velocity of which blood cell, which red blood cell?
That's the instant, no, that's not the blood cell, that's the bulk flow velocity. So the instantaneous bulk flow velocity that you have in this branch or in this branch here. So it's not the red blood cell velocity, because I mean, we're going to come to the Farrier's effect a little bit later. That's a little bit larger, but the decisive factor is really the bulk flow velocity for the red blood cell where it goes. And because the bulk flow velocity is the decisive factor where the red blood cell goes, that means that, that's also the velocity that gets balanced. Does that make sense? Yes. Yes. Let's continue. Yes, as I said, that's one of the things which we also wanted to study in more realistic network. And we did this in these networks, which you've seen before, where we also looked at the pressure boundary conditions. And in order to study the self-regulation in these realistic networks, we defined the bulk flow velocity difference, which is basically just the relative velocity difference at a divergent bifurcation. And then we decided that if that velocity difference is smaller than 20%, then we assume that this bifurcation is well balanced. And based on that, we can then compute the degree of well-balanced bifurcation. So that means the number of well-balanced bifurcations in comparison to all divergent bifurcations which we have in the network. And we can do that for different kind of networks. Here you see an example for also a very simple honeycomb network where we have again the bifurcations, and you can see it here on the right side for the simulations where we don't have any red blood cells, and you can see it on the left side where we have an inflow hematocrit of 0.3. And you can clearly see that the number of bifurcations where we have this balancing of outflow velocity increases significantly if we have, if red blood cells are present. What you also see is that, of course, we still have quite some bifurcations where we don't have a balancing of these outflow velocities. And that is simply occurs, as I already mentioned before, it might be bifurcations where we simply didn't have sufficient red blood cells to compensate the differences in outflow velocities. Thus, of course, the balancing is not perfect, but yeah, it occurs quite apparently. We did the same study for this realistic network. Here, again, the more heterogeneous the network becomes and the more heterogeneous the outflow velocities becomes, the more of these unbalanced bifurcations we have in our network. But also here we see a clear trend and a clear increased degree in well-balanced bifurcations for the simulations with an inflow hematocrit of 0.3. What is actually also interesting, what we also tried doing, is that you can increase this inflow hematocrit, for example, to 0.4 or 0.5, and then you have more red blood cells in your system. And that actually helps to improve the degree of well-balancedness of the system. But again, you reach a point, kind of an optimal point, regarding this balancedness, because if you have more red blood cells, then you get traffic jams and accumulation of red blood cells, and also then you don't reach a perfectly balanced network. And what was actually interesting in that study as well is that the ideal hematocrit seems to be in the range between 0.3 and 0.4. And that's actually the hematocrit which we know we have in the human or in the living animals as well. And well, that kind of confirms a little bit that there's also an ideal hematocrit of how many red blood cells we actually need in our vascular networks. We also did some in vivo studies on that, and actually it turns out that also there in divergent bifurcations or also in silico studies, you see this trend happening. Here's just another example of a simulation, how it looks like again. Again, a simulation with red blood cells and a simulation without red blood cells. You note that regarding the pressure field, you don't see a very big difference. What becomes interesting is if you look at the hematocrit again, here you see the same trend as in that animation before. We have many plugged capillaries here at the side. And where it becomes really interesting now is if you look at the tracer concentration. Because in the simulation with red blood cells, we have the higher flow velocities here. That's why we get this kind of flame-like shape if we enter a tracer into the system. While in the simulation without red blood cells, you see that our tracer profile, well, it's more like a circular shape. And yeah, so you can definitely say it is important that we consider the red blood cells for our simulations in microvascular networks, because they do play a role, first of all, for the flow rates, but also, for example, if you would simulate drug concentrations or something like that, it's really important that we account for the effect of the red blood cells. Yes, the third red blood cell related flow phenomena, which we didn't talk about yet, is the Farreau's effect. And we start again by looking at our flow profile, which looks like that in an ideal pipe. And we have a mean velocity. However, if we think again about our red blood cells, the red blood cells need to squeeze into the capillary. And that also means that they travel in the center of our capillaries. And that again means then that if the red blood cells travel in the center, they are basically exposed to the highest velocities which we have here. And this causes that on average, the red blood cell travels a little bit faster. That's kind of the red arrow for the red blood cell and the blue one for the bulk flow than the bulk flow. This effect is also generally important. However, it doesn't have as dramatic consequences as the interplay of the bifurcation rule and the Farreau's-Lindquist effect. Nonetheless, it underlines that we really have two different phases in our system that we need to account for. Yes, and we talked a lot about red blood cells and the bifurcation rule and phase separation, but of course that is all still a simplified model, and not everything is described here yet. And one thing, for example, that is well established, which is also present, is the so-called endothelial surface layer or endothelial glycocalyx. And that is what is positioned here at the vessel wall. And it looks a little bit like seaweed, what you have here. And the seaweed also means that the red blood cells actually don't totally reach the vessel wall. You can also see this a little bit here, and that you can have a little bit of gap between the red blood cells and the vessel wall. And this also means that well, the different theories, what kind of this endothelial surface layer does. So one theory, for example, is that it acts like a lubrication film. However, it can also be that the endothelial glycocalyx gets activated and that it actually, that the red blood cells kind of stick to it. There are also simulations who look a little bit how the red blood cells, how the red blood cell shape or the red blood cell speed actually. If the red blood cell travels faster, they tend to kind of push away the endothelial surface layer because it's a very soft structure. And then how it kind of deforms differently, the red blood cell, depending on the interaction with the endothelial surface layer and the glycocalyx. And yes, as you can guess, all these effects, so basically what happens between the red blood cell and the vessel wall, all these effects, they in the end will affect how the red blood cells increase the resistance of the vessel. So that's actually something which is not super easy to study in vivo, and it's also difficult to study in simulation, just because there are so many different biological components and biological interactions taking place. However, what we do know in any case is that yes, that the red blood cells increase the resistance of the vessels, and the more red blood cells you have, the more the increase in this resistance will be. However, the precise factor, that is something which is a little bit difficult to determine, and that's just things which you have to keep in mind if you do simulations and if you want to interpret your simulations. Yes, I'm going to come to a little bit summary of what we did so far before I show you two examples of the research which we did a little bit. Yes, so first of all, I showed you how we can set up a blood flow model with red blood cell tracking, which basically allows us to compute the distribution of red blood cells in such a large networks and the flow rate in such a large network. I hope I convinced you that for that goal, we don't necessarily need to resolve the deformation of the red blood cells, because what we're interested in is really just the distribution. Thus, we don't need to resolve all the effects there. That is one of our key assumptions, but I think bearing our goal in mind, that's a very valid assumption. The second aspect, which is very relevant, is that we are in the Stokes flow regime. That means that inertia basically doesn't play a role for the simulation. And again, as long as you're looking at microvascular structure, even if you would have a few pile vessels at the surface where you're kind of just about in the Stokes regime, that assumption is also valid and well, helps a lot to set up these simulations. The model which we derived, it accounts for the bifurcation rule, and it also accounts for the Favreau-Lindquist effect, which is the effect on the resistance, and also on the Favreau's effect. And also that is very important to keep in mind, that we really need to account for these effects in order to understand the flow field and the distribution of the red blood cells in these networks. And if we neglect this effect, we might not get an appropriate picture of what is happening in these networks. As I said, in every simulation, there are uncertainties, and in every numerical model, there are uncertainties. What is important here is that you're aware of them. And for our setup, the main uncertainties are the empirical relations to describe the red blood cell related flow phenomena. As I mentioned, the general trends are very clear here. So we know that the splitting is different, and we know the impact of the resistance, but we don't know exactly the precise range we're in here. The empirical relations which we use for the simulations, they're mostly derived in animal experiments, but there are always some uncertainties in measuring velocities or measuring flow speeds, and that can affect our simulation results. So we have to keep that sensitivity in mind. Another uncertainty is the boundary conditions. Again, we have many in and outflows in these networks. However, I guess we did a good approach because we tried to, assign the pressure boundary conditions based on increasing our network size. And actually in those whole brain data sets where we have an entire network, that's also one advantage of them, because if we have a very large network where we just have 1 or 2 inflows, we actually are also able to completely eliminate that effect or that uncertainty regarding the boundary conditions. And the last thing, which is a sensitivity of our simulation, is that the diameter estimates in these realistic networks. Because of course, it's not so easy to acquire such a network in the first place. So what is normally done is that you perfuse a brain with some filling, and then you scan the brain, and afterwards you have to do some segmentation and reconstruction. And it's actually regarding the image analysis, it's quite evolved. And of course, again, there you have uncertainties. And if you remember Poiseuille's law, where the resistance is affected by the diameter to the power of 4, you can imagine that just small errors in our diameter estimates might actually also play a big role for our simulation results. That's why it's very important for simulations as well to have as good diameter estimates as possible. Yes, and I want to finish with actually 2 examples of the research which we did, and just to give you a little bit idea about what we can actually do with that. And I want to start with one example of the work which I did. Yes, and as I said, we simulated blood flow in these realistic networks. And what I actually looked at is basically at which level do the red blood cells enter the brain, or where do they leave the arterioles and enter the capillary bed, and where again do they leave enter the venues? Because the blood enters always from the surface. And what I actually found is that within the capillary bed, the red blood cells tend to move in planes. So they really go down to a certain level, for example, here, then they stay more or less in that plane, and then they go up again. So we have kind of this laminar perfusion of the capillary bed. And within the capillary bed, we don't have too much different directions in flow. So it really always kind of goes in one direction. And if you think a little bit about the pressures which we have in these penetrating vessels, it's also plausible, because the blood cell actually always goes into that direction where we have the highest pressure gradient, and that is more or less perpendicular in this plane. And that is, for example, interesting because if you do imaging now, it's good for you to know, or easier for you to know, that the flow tends really to have this kind of U shape. So always down in capillary bed and up, because you can really focus on different layers. And you also know that, if you say flow changes up here, that probably doesn't matter down here. And so you have this different, this layered perfusion of the capillary bed or the vascular networks, which can play a role for imaging, but also for regulation, because we actually also have different neuronal densities in the different layers. And that's just one example where we could basically help with the simulations to look at that. Another example which I would like to give is shown here on the right side. That's now work of a PhD student in our group. And that's actually an interesting characteristic of the mouse brain, because in the mouse brain, we have the so-called barrel cortex. And these different barrels, that's basically each of these barrels is associated with a whisker of the mouse. So that's really kind of different neuronal regions which are associated with different whiskers. And what you see, what we studied now is basically how would we need to change the vessel diameters in order to increase the flow in all capillaries within such a barrel. And what we did in the study here, we used an inverse modeling approach for this study, is that we actually could show that in order to get such a localized increase in flow, it is necessary that really capillaries respond. If we only have arterioles that respond, the response would be like that. So basically we get a flow increase in the entire network. However, if we have capillaries that are also allowed to respond, we manage it very well that we only have an increase in flow in the central area here, where we also have the barrel in our network. Yes, that's it about the two research example. And last but not least, as I said, I'm going to transition to the University of Bern in summer. So if some of you finishes his studies and wants to do a PhD, yeah, I'm looking for PhD students. You find the advertisement on the webpage of the ARTOC Center in Bern. And yes, if you're interested, you can contact me or yes, just ask. Yes. Yeah. Do you have any questions?
The slide that you were talking about the coefficient of the matrix coefficient, the coefficient matrix crossing the pressure.
Sorry, which slide you're in the first part?
Yes.
You mean about where we solve the whole system?
No,
this one?
In practice.
Yes.
The number of pressure nodes or the number of
yes.
nodes that you implement this equation. How much of these pressure exactly exists really? You know, I mean, when you want to take the inverse of this matrix, it's very important to know the size of the matrix.
Yes, exactly.
I just want to know in practice the diameter of this coefficient matrix is the order of this matrix is, for example, 1000 across 1000.
Yes, I mean, in the end, it really depends what kind of network. So the little square ones in which I did most of my simulation, that one has about 20,000 nodes. And yes, but that is still can be solved very, very easily. I was mentioning these whole brain microvascular networks, and there you have, I think, 4 million nodes. But still, if you just solve the flow field and you just need to invert this matrix, that can also be done in a few seconds. But of course, in these very large networks, for example, then it becomes, so I mean, it's not very optimized simulation code, but for example, in the networks I simulated about 1 cubic millimeter, until I get a steady state regarding the red blood cells, it runs about 8 to 12 hours. So it really takes quite some time until red blood cells are distributed like they should be. So it really depends. If you just solve the flow, it's not very expensive. But if you add in the red blood cells and you need to distribute them, it just takes time until the flow really evolves. And then that's what really becomes computational expensive, even without resolving any deformation of the red blood cells. Just tracking all these particles becomes very computationally expensive. Then that's why it's also not possible yet to do that in these whole brain reconstructions yet.
As you said, you use iterative method.
Yes, I mean, I used an iterative method there. Yes, I mean, it's the code we use is written in Python, and you have the different SciPy packages which you can use there. And yes, but there's specific ones because you also have a sparse system here. So there's specific solvers which are more suitable for sparse systems, and you can use them. And then yeah, it takes a second or something to really solve that. Yeah, so really the tracking is the computationally expensive part. Yeah. Any further questions? If not, then thanks for your attention, and yeah, you'll learn more about the modeling from Aurelia soon.